Hi, everybody. So we'll start the Aerospace Test Bench webinar today. It is about develop, test, and validate your all ECU. So today we'll have actually two presenters, myself, Matthew Eno. I am the offering manager of the Aerospace at OPAL-RT technology. So basically, I'm managing the coordination of all tools that OPAL-RT is doing, actually, and doing also the marketings for the aerospace industry. So I'm really here to listen to you, as a customers, and actually make sure that OPAL-RT can bring our tools and our services up to speed to your needs. And I will be also assisted by Alexandre Leboeuf. So Alexandre Leboeuf, are you there?
Yes, I am. Thank you, Mathieu. Hi, everyone. So you're hearing me well, I presume?
Yes, it's working.
Excellent. So again, thank you, Mathieu. So yes, my role at OPAL-RT is Customer Solution Division Manager. Basically, it's coordinating the customer support effort throughout the world. Specific custom project management and custom project engineering team also is part of the group that I manage. Basically, it's the one-stop stop for customer experience, basically.
So today, we have as an agenda, we'll have a short introduction about the concept of actually developing and test your ECU, actually a test bench. And today, really the goal is to pass all the key concepts that will bring up to your needs, actually, and build the ECU and actually all the question that you should ask and actually all the development stage to actually achieve to a final test bench. So we'll start with the initial requirement and concept of a test bench. And then after that, we'll understand actually what is required or not for testing the device under test, the UUT, we call it. And then we go through a design phase of the test bench. So this is where we ask actually the question, how do we do the test bench to actually achieve our goal? And the consideration that we need over the real-time hardware and software. So what tool that you have to select at the end to make your project a success. Then we'll do a recap on the OPAL-RT mission on those topics, like how we can help you if needed. And we have a question period about your project. So don't hesitate at the end of the webinar to ask us questions. So if, as an introduction, the goal of this presentation is actually to let you ask yourself question for your test ECU. So basically, we have a lot of experience at OPAL-RT. I've been working actually with Alex for in this team for many years in one of the team for the services of the customers, and now I'm the offering manager. So I'm really want to bring my experience to the company. So on this webinar, what our goal is really to share our experience of a lot of benches that we did, and actually a lot of customer that we work on. And some quick facts and question and situation that we saw before. Because the real first goal of doing a test bench to test your ECU is finding error and search during the test and the certification phases of a test bench as close as the lab and the production lab possible to make sure that as early as we find some error or we can fix them, the cost will reduce a lot than actually waiting later on the process to test the ECU. So basically, after saving a lot of costs, the impact of a test bench is really to accelerate the design phase between the R&D and actually going to the production and certification. So this is a mandatory phases to use a test bench to do certification on an ECU and a UT in the aerospace industry. The goal is also to improve quality for sure. Okay, so the closer, the earlier we can find any issues in the unit under test, actually it would be the easier to fix or to improve the system. So the quality will be improved as well. We'll have also expandability. So we want also like test bench to be easily upgrade and actually be able to do some replica to actually like extend the testers on different front. So in aerospace, especially like when you have a program for a new ECU, usually we have more than one benches because there's not only a single team that will test the systems, and that will bring to us like a lot of speed and agility in the test and the certification. So if we look at the TRL, like the technology readiness level, really we saw the bench starting around TRLR 6. So basically the R&D is do its job, like we do the research, we start having prototype. So we're getting closer to have like a workable prototype fully assembled, not just the breadboard. So at TRLX 6, we start using the test benches with the HL systems. At TRLX 6, I would say like it's more an R&D benches. And more we go forward toward TRL 7 and 8, we came across with more like benches for certification and actually maintenance at the end of the day. So the story that we want to propose today in this presentation, like it's really like going through you a story about like how do you design a test bench. So the first step that you ask is like to really define your requirement. So like it's really for you to understand what is the bench life cycle that your bench will have when you will design it. Then after that, like really ask you like what is the test that you want to achieve with your system as a test synopsis. And also we want to share information about the project cycle. So all the projects that come in like points together. So like we see a lot of them with different customer, but like we can regroup like a larger story about the project cycle. And then we have the UT definition as the IECD. So this is really the starting point for the design where the IECD like will define like how to connect the UUT. So when we have this information, we ask ourselves, okay, how do we really want to connect the UT to our test environment, like our test bench? So we'll ask our question about like fault injection, breakout modules. Do we want to test a single ECU, or we want like a flexibility in the test bench to actually have different program associated to it? And also like, how do you prioritize these signals? So basically, like asking ourselves a question is all signals will be needed for the HL system to be tested. Then after that, when we understand how to connect the UT, we go to the test bench phases. So like how do we design the test bench as the wiring? Do we require some special conditioning? And actually, what is the ergonomy of the test bench that we're looking for? Then, including in the test bench, we can go to the real-time platform. So defining what is the real-time platform requirement, like what is the performance, what kind of IOs we need, and especially what kind of communication. Aerospace Test Bench are heavily based on communication signals as well. Then we go to the model development. So when we have all the hardware done, we need to think also about the software, so the model development. So what kind of tool are you looking for, a suite of software that will let you do the model design? How do you manage your models? And also, how do you control the real-time platform that will control the bench itself? Then we need to think about also who's going to operate the bench. So when we design the model, the job just started. Like now we're really getting into the jobs and we do the certification or test on the UT. So what kind of tool are you looking for to be efficient in the visualization, the data recording and scripting for the operator to be efficient in his job? So we'll start with the first step. So the initial test requirement, and I will let Alex Leboeuf to talk about his initial test requirement.
Yeah, thank you. So as far as most test benches in Aero are concerned, the usual life cycle that we've seen throughout the years is that a test bench in Aero has the longest lifespan of almost all test benches that we've seen in any market. This is mostly related to the fact that once an airplane is airborne, it is usually manufactured for a lot of years. We're thinking about like in the 20 years plus. So usually the test bench needs to follow the aircraft in that lifespan. Obviously, not necessarily all test benches will last that long, but there are certain types of benches that you'll see that I want to present to you today. The first one is basically the most involved system, the most precise, that has the most definition inserted in it. Most advanced equipment is also, and it's the full R&D or rapid control prototyping benches. Since they are the tools to make sure that what you've designed is on par with the specs expected by the airframer for the certification effort and their requirement as per se for the aircraft. Obviously, you'll need to test everything more thoroughly to make sure that everything is in working order. Now, since those benches are usually the most expensive ones, it's not necessarily the benches that we want to send to our service providers that will test subsystems of the controllers that we're going to be designing. So in this specific case, what we will have a tendency to do is to do scaled down versions. And those scaled down versions will focus primarily, not necessarily on the specs, but on the functionality themselves. So it's going to be the systems that will have the most simulated item in it, so as to drop down costs and to make it more easy to maintain later on. The certification bench is basically the next evolution of your R&D bench. Once you're done on your level and you're pretty much validated all the specs, well, your next step basically is to get the certification on your hardware and software. So you're going to be able to use the bench to be able to do just that. And finally, last but not the least, is the maintenance and support role. Basically, we don't usually sell new benches for that role specifically, but it's more like a transition of your R&D bench or the scaled down versions that will be used that are transferred to that. And the purpose of those benches is, since at this stage the aircraft is airborne and is flying, it's primarily to find bypass in errors that the pilots see while during operating the aircraft, because well, maybe you know not, but a lot of the aircraft right now that are flying aren't necessarily foolproof as per se for errors, but all the pilots know the effective bypass to prevent having to go through the certification process again. And it is not life-threatening. It's just a matter of bypassing some of the subroutines so as to bypass a bug and reset to a generic and full operation mode. And those benches at that moment is specifically to be able to find those. So Matthew, if you can change the slide, thank you. So now that you've focused a little bit on what bench you might want to have, it's like the purpose of the bench, you want to focus on what you're going to be testing. So it's really important to scope the list of tests that you will be mandatory for your bench, the planned bench, to be able to have a great success with it. Because some faults that you may want to validate may require subsystems that aren't part of your system in itself. So you'll have to think a little bit outside the box to add some hardware, for example, or some software subroutine that will create some events that your controller obviously won't be able to do by himself. Or the hardware that you're going to put in the bench that is related to the aircraft might not also be involved, since usually you don't break a torque motor, for example, for a purpose of a test. You're going to simulate it. So to be able to do that, you need to really think about the faults that you want to do. So the list of tests also will probably define a little bit the environment of the design that you'll be using and where your test bench will be set up. Thank you. Now a project cycle. Okay. In Aero, we are all pretty much acquainted with project management. It's part of our daily life. For test benches, we don't do anything different, to be honest. So the key words here is plan ahead. Why? A lot of equipment require long lead times to be able to arrive, and we want them to be able to take into account that into your timeline, so that way you don't get sidetracked by delays. There are some equipment also like GNSS for the GPS control and simulation of the star maps that may be used by your system that requires some sort of government approvals. So this also, we all know that governments aren't necessarily focusing on industry requirements. So sometimes it may take more longer than we would like. So it's always good to plan ahead and integrate this inside our program. Here, what I'm showing is basically a step down version of an Aero project management milestones, like the preliminary design review, PDR, CDR, which is the critical design reviews, are things that you should be eligible about in the aerospace mode project management. But what we've done is that we've stepped it down a little bit in the criticity and the different documents to be provided at each milestone to be able to be more flexible. Because let's say, for example, you're doing a design for an R&D bench. Well, usually your controller is not finally designed yet. So your specs might be evolving as the bench is being built, as the design is being done. So you need to be able to account for that in your project management to be able to prevent costly changes later in the program. Also, it's not written here, but in the timeline, but you definitely need to have an ITP, integrated test plan, added at the reception of the bench in your premises. Why is that? Is because as good as we are, as our intentions are, we go and evaluate everything to the smallest details. There will be always something that will differ from the reality. So it's not uncommon that the specs that were given are not necessarily matching the design of the ECU that was done, and we need to make some adjustments before going to the actual test phases. So you need to plan for an integrated test plan before starting your tests. Next slide. So on to the EICD. So the EICD stands for Electrical Interface Control Document. Usually it's an Excel document that will list all the ECUs IOs. Airframer usually use those for all the subsystems that will be present in the aircraft, so as to be able to monitor everything on a versioning level. Why the versioning level is to make sure that everybody's working on the latest version and not have the engine provider working on version 1.2, the air management system working on version 2.8, and in the end they don't match up. So that's why the electrical interface control document is so critical to the bench design, is because it follows the airframer and your customers and your providers on a single point of the design of the controller. Usually what we're going to want also to be showing in this document is not only the mnemonics, so basically the names of their signal, but also their signal types. For example, you have like RTDs for sensor temperature. Let's say with the Excel, it's going to be super easy to see that you have like 26. And that in the next version, you have like 28. So it's important to be able to have those details, so that way it puts everybody at ease and in the know about what changed and what's the next evolution into the evolution of your ECU, basically. So
I would like
yeah.
to point it out that during all my experience in integration, is like the sooner we get this document, the faster we can get across all the process of creating a bench. Because like if we don't have this at first, early in the stage, we will like just take the time to build this kind of document to make sure that we all talk the same about the same thing. So we will like service provider as OPAL-RT can work with you to build it. But if we start with a document that already exists, that saves us a lot of time and actually a lot of confusion. So it's really a key document that we base all our design on it.
Yeah, that's true, Mathieu. And if for any number of reasons you don't have such a document in your templates, don't worry. Most integrators should be able to provide you with a template of their own to be able to start with. And that can be done as early as the quoting phase. So you can ask your sales representative of the different integrators that you're in communication with to be able to provide you with such a template. It's going to show you also a little bit on the seriousness of the integrator and how involved they are in the aerospace industry, because it is the starting point of the design of the bench, literally, like Matthew mentioned.
So the next step in our like presentation is the utility connectivity. So now we have the initial test requirement. So we saw what we need. Now like we can start thinking about like what a test bench will look, and we start with the connection with the UT with Alex.
Yes, what we can see here to highlight the connectivity that is present in the bench is on the left, a typical configuration of some of the boxes that will interact together. The control unit or ECU is at the bottom of this typical configuration, and you have an example on the right of a test bench that was done by OPAL-RT. But most test benches are pretty look-alike. So it's a good representation of what you will be able to see whoever manufactures the bench. So rapidly, what we will have in there, and I'll go a little bit more in details of each of the different items, but you'll have the controller, obviously, but you also have the simulator in itself, conditioning units, because the IOs aren't necessarily always a direct connection, different loads, and the fault insertion unit and breakout box, which brings me to the next slide. So basically, before getting in the FIU and the fault insertion units, one part that we want to focus also is to know how your controller will be interconnected with the bench. Why I'm saying this is because sometimes you have a multiple program approach and the bench will be using different controllers. Maybe you have a hardware upgrade rate, so you'll be swapping the controller really often. So you need to take that into account how you design it. Perhaps you'll have a multi-unit under test configuration like the picture on the left. What you see there is a configuration for 3 controllers. So on what we call an A-rank chair. So basically the top part is completely removable with 0 insertion force connectors. So that way you can just design a specific chair for the controller configuration you have and connect it to the bench while having the generic interface. So the generic interfaces brings us to the newest trend in Aero, which is the generic test benches. Okay, we've seen in the previous slide a test bench that was comprised of only 1 cabinet. But the trend now is to be able to design 2 cabinets. The first one that will have the core of the simulation and a generic number of different type of IOs or subsystems. So let's say 18 leak detection loops, PT500, let's say I have 50, and the like, so as to fit most of your configuration that you'll be having for presently in the future. And you have the second cabinet that will be the specifics. So the loads pertaining to your system, so torque motors and stuff like that, or the ECUs themselves with such A-rank chair to interconnect the controllers.
So if I can add also for the generic test benches, the main idea that we see a trend like for the last few years, like we saw the cycle of the test bench. So when all the certification is done, like the bench go to like static configuration where it's there for maintenance. So if something happened or they need to do recheck something, they will like actually reconnect the bench and like restart using it. But this bench actually cannot be used for like many years. So what they want as during test benches is a flexible part where all signals are generated as a generic thing, and this part actually could be moved from program to the other program. So like they will have like special configuration for one ECU or one UUT, like a program, but like the main real-time part and like the conditioning could be something that be reused on different parts. So basically, like they see that there's a lot of cost of money to actually like not hold like a part of the bench stick to like a whole program and take the generic part of the benches to be moved around between different programs. So this is the idea of generic test benches.
Yeah. And to add also a little bit on that, is usually in the maintenance phase, the benches aren't used 24 hours, 7 days a week. So it gives us the opportunity to probably leverage that purchase or that design to be used somewhere else when we have the generic test bench approach. So now we're talking about the FIU. Mathieu, again, yeah. So the FIU, or fault insertion unit, basically is one of the most interesting feature that you can add to your test bench. Why? Because it's automatable for your electrical tests. So this gives you the opportunity to program via scripts a wide range of different tests that you might want to do on the electrical front. For example, you can want to have a simulation of an open signal, an open wire, so as a loss of your sensor, for example, and see how the controller reacts. Also to short two signals together, again, to see how the controller reacts, and so on. This usually is to validate all the cases that hopefully will never happen in the aircraft, but sadly may happen once in a while. And we want to ensure, obviously, that the controller won't go haywire and do and drop in safe mode and stops the engine, for example. So that's part of the game to be able to test. And also the fact that it's automatable permits you to save your test engineers to be able to do the analysis of the results that will be generated throughout the night, for instance, or throughout the weekend. So that way you can have a focus on your engineers as to really do analysis where their time is most well spent than to actually manually connect wires to generate the errors to see what's going on. So that's why the FIU usually is the most interesting part to have in your bench. On a side note, though, is usually one of the most expensive item per line. So what you'll want to do at this stage is usually to do a selection of what signal has the most value to go through it. So for example, we use, let's say on the left, we have a Pickering FIU card for high current signals. Well, if we want to do some tests on the power lines of the controller, it might be super critical components. So that makes sense to have it in the bench, but certain temperature sensors aren't that critical to be validated, and if we lose them somewhat, the controller will still be able to manage with encoded values, default values, and will still be able to work. So this one might be able to be done manually, so it's not necessarily critical to have it in the automatable box. So on this front, you can save on the cost of the FIU for that purpose. The next step is the manual breakout box, which is basically a little bit like the fault insertion unit in a sense that it permits to do the same test. So you can manually short two wires together, insert different type of noise signals For example, you want to validate the impact of the injection of a 60 hertz wave on the monitoring of the alternator generated signal. So you can send a signal on this manually through the breakout box. So that's the counterpart that is cheaper to the fault insertion unit. But again, you have to have your engineer perform the test, or your technicians, to be able to perform the test manually on this front.
And if I can give you an
Yeah.
advice, like I will probably say that it's almost mandatory to have like a breakout box like that, or actually a certain way to access some signals during commissioning with customers. Like that saved me a lot of trouble many times. Imagine yourself, like a controller have many buses of communication. For some reason, one of them get damaged or doesn't work as you expected, and you want to test that. A breakout unit like that make you an easy connection without like actually opening the test bench to actually like isolate the bus and actually maybe just with wires swap two buses internally in the bench. That's something that it could be really useful. You want actually just probe what's going on in the signals. You're sending like signals like for like let's say temperatures, and like the temperature is offset of 10 degrees in the reading of the controllers. What's going on? You want to demystify where is the problem. So is it the signals that are not good? Like maybe the test bench doesn't do the right signal, so you know what you're expecting. So with an oscilloscope or multimeters or whatever tools, like the breakout box lets you have a quick access to the signals and measure it. Same thing as adding like a quick filter, like like you have noise on the signals for some reason that you didn't expect it. With a breakout box, you can mount like a small setup there, just as prototype, to actually do a filter, and maybe like that will correct and adjust the test bench for that. For sure, once you find a solution, you will probably incorporate the solution as a fixed solution in the test bench. So basically, you will open the test bench and add this component. But the breakout box give you like an open access to all those signals to actually like advance quickly during the phases. So I cannot like strongly advise to include like some of those breakout modules in your systems during
Yeah.
your design
Well,
phase.
Mathieu, you're right in a sense that the breakout box is one of the most powerful tool for debugging the bench and your system, as it gives you the opportunity to open up, if we can say so, the system and the signals without having to cut wires, or to be able to have to open boxes, or to actually monitor on the ECU itself. So it's like the FIU, that is a super powerful tool for automation and save time. The breakout box is a tremendous tool for debugging your bench. So much so that some of our customers have been designing mobile breakout boxes, so that they're not like the example shown here, rack mountable, but are actually small suitcases that you can move about and interconnect in the different benches. So that way you can save on cost while having one set of mobile breakout boxes, for instance, and after that reuse them on different benches. The only thing you need to keep in mind is that you need to have the same type of connectors to be able to connect to the different test benches, or do patch harnesses to be able to interface, depending on how is your design approach and how you're managing the benches that you have in house. Okay, so it's something that you don't want to live without. You could probably manage without an FIU, taking more time, but the breakout box is one of the best tools to for the engineer. It's the engineer's best friend in test benches.
I agree to that. Okay, so let's conclude the connectivity. So after that, when you set up like the way you want to manage the connection with the UT, is like we're going deeper as the test benches itself. So the test bench is the more static part of the setup. So where you have wiring, conditioning for some signals, and like actually really thinking about the bench ergonomics.